as you'll see, if you do watch it on YouTube, Chiara is a star, and she studies stars that are exceptionally interesting, or dead stars, or corpses, stellar corpses. I don't know. In any case, let me just check to see if we're live. And assuming that we are, we can start this phenomenal discussion that I've waited years to have with Chiara, because I've been a big fan of her work. Even tried to get her to come to UCSD, but we won't talk about that. Those are painful experiences for me. But she's truly an exceptional scientist, a good friend of many of my colleagues and myself in the field. I'm going to play in the background. Let's see if this will work. This will be cool if it works. Share screen. Open. Chiara, can you hear me? Hello? Chiara? She's in the green room. Hold on one second, everybody. Getting this all queued up in real time. This is real-time science. And now it's asking me for passwords. Let's see if that will work. No. Cancel. Sorry. All right. Guess is in the green room. Chiara, can you hear me?
Yes, I can hear you now.
Okay, good. All right. For some reason, it was putting it in. I want to go back to camera mode. There we are. Hi, Chiara.
Hi.
Hi. Sorry about that. It's always fun to do live streaming. Oh, they're actually doing it. They're actually showing it. Oh, no, that's your video. So there's an amazing, amazing video that NANOGRAV has put out featuring our own guest, Chiara Mingarelli. Am I saying that right? I'm always confused.
It's a hard G, Mingarelli.
Mingarelli. It's good to see you. It's good to be with you. Thanks for joining the Into the Impossible podcast.
Yeah, thank you for inviting me.
So I've, of course, followed your career for many years and been fascinated by the stuff that you do. I first want to say to everyone who's listening on Clubhouse, you can watch the fun on YouTube, Dr. Brian Keating. We are streaming from there. And if we have time, we'll take some questions. We're on a little bit of a tight time schedule today, but that shouldn't deter you from asking any burning questions. I'll certainly have time to take maybe one or two. But today we are going to talk about this interesting discovery that has huge implications and a little bit of frustration for me, Chiara, because as you know, I build a gravitational wave detector that's a huge, telescopes and so forth that detect the signal via the cosmic microwave background, we hope. And here you are outdoing me, building a galaxy-sized detector of gravitational waves. First
Go
of
big
all,
or go home.
That's right. So can you introduce yourself, who you are, where you are, how you spend your time on planet Earth, and tell us about the lovely University of Connecticut, which, as I was mentioning, is where the alma mater of my beloved mother, Barbara Keating. So Chiara, tell us who you are.
Who am I? I'm a gravitational wave astrophysicist. I'm originally from Ottawa, Canada, and I've done my studies all over the planet. So I did my undergraduate degree in Canada and then graduate work in Italy and then the UK. Then I lived in California for a while, and then Germany, then New York, and now I'm an assistant professor here at the University of Connecticut.
And you have another kind of part-time job, or maybe sometimes it's full-time job, and that's as a research fellow or scientist at the Flatiron Institute at the Center for Computational Astrophysics in New York City, which is a project of the Simons Foundation. Tell us about that, and what do you do there?
So at the Center for Computational Astrophysics, or CCA, as you said, I'm an associate research scientist. So I think about how supermassive black holes merge and all the different ways that they can merge and emit gravitational waves as they're merging. And then try to figure out how all of this happens using these supercomputing facilities there that are really one of a kind. So it's a huge resource and benefit to my research to work there. I also am really plugged into the New York community there. So not only is CCA a wonderful place in of itself, but it also hosts really big communities. So we have colleagues at Curie, Columbia, NYU, Rutgers, Princeton. It's a real nexus of people coming in and out, or at least it used to be. Those are my last memories there, which were almost a year ago at this point. Right now we're all working remotely, but hopefully we can go back soon.
Yeah, that's right. The city has become a very different version of what it used to be, but I have many fond memories of seeing you work in your cubicle along with all my friends at the CCA. It's really a fantastic organization and really unlike any other organization of its kind, to my knowledge. So it's very impressive how far it's come in such a short period of time and how it continues to grow. As I said earlier, I wanted to talk to you for a while, maybe over a year, and then I was like, "Well, this announcement that was made just about a month ago really set the astronomical community abuzz," and I felt like it would be wonderful to have you on the Into the Impossible podcast to tell us a little bit. First of all, starting from the very basics, what is a pulsar? Why are they interesting? How do you build a gravitational wave detector from a network of pulsars? And then what the discovery that you guys announced back at the AAS meeting is all about. So first of all, what is a pulsar? Why should we care? How does it affect Joe Bagadone? No, I'm not going to say that. I hate when they ask me that question. Yeah, don't dumb it down, but please, yeah, what is a pulsar? Why are they so fascinating to you?
Sure. So a pulsar is a neutron star. And a neutron star is a dead core of a star that was about 10 to 25 times the mass of the sun. So when the star dies, it goes supernova, and what's left over is this neutron star in the center. So there's so much pressure during this implosion, during this supernova implosion explosion event, that the protons and the electrons get squished together to make this ball of neutrons. Now, there's not enough mass for it to continue to collapse into a black hole, but there's enough so that about 1.4 times the mass of the sun is squeezed into a space that has the diameter of the island of Manhattan, for example.
Mm-hmm.
So something that's the size of Manhattan has 1.4 times the mass of the sun in it and spins around hundreds of times per second. Those are the objects that we use as gravitational wave detectors. So the way that we can do that is because the spin axis of the pulsar is misaligned with its magnetic field line. So if this is the spin axis and then the magnetic field line is this way, then every time it spins around, it sends a flash of radio waves towards the Earth. And each one of these flashes is very regular. So we know exactly when the flashes should arrive at the Earth. And of course, we measure when they do arrive at the Earth. And the difference between when we expect the signal to arrive and when it actually arrives could signal the presence of gravitational waves. Now, that's because gravitational waves change the distance between the Earth and the pulsar. And so gravitational waves stretch and squash the fabric of space-time, right? In this kind of plus fashion or in a cross fashion. There's more if you believe other theories of gravity or extensions to GR. We can probably talk about that later.
Yeah.
So the important part, though, is this time advance or delay, depending on if you're being compressed or stretched out. And that's what we can find using these ultra-stable millisecond pulsars.
And so how did the idea of NANOGRAV, how did that come to be? What was sort of the impetus for it? And how is it designed, quote unquote, to do what it's doing?
Well, the history of NANOGRAV and of pulsar timing really goes all the way back to the discovery of pulsars in 1967 by Jocelyn Bell and her collaborators. She was one of the first people to discover pulsars, and then millisecond pulsars, which are the ultra-stable version of these, were discovered in 1982. So in fact, not that long ago. The idea, though, of using a regular signal and changing and trying to change differences in the arrival time in the signal goes back to 1975, when some scientists at JPL proposed to do this with the Pioneer 10 spacecraft. And that was an amazing idea. They were the ones that proposed it, like, oh, you know what, this spacecraft is going really far away. And actually, if we can detect changes in the arrival times of the signals from this spacecraft, then we might be able to look for gravitational waves. And so by using these ultra-stable millisecond pulsars together with this idea of changing arrival times, we can come together with this idea of pulsar timing arrays. But I mean, it really took a lot of people a lot of time to get the idea off the ground. The work that I think is that forms the basis of our current collaboration is the 1983 paper by Hellings and Downs, who really had the idea of cross-correlating all of these millisecond pulsars to look for a gravitational wave signal that's common in all of them. So NANOGRAV in itself started about 13 years ago, and the idea of pulsar timing arrays, of course, is much, much older than that. So NANOGRAV is only one of the pulsar timing arrays that exists around the Earth. There's also the Parkes Pulsar Timing Array in Australia and the European Pulsar Timing Array. And there's some emerging pulsar timing arrays now, the Indian Pulsar Timing Array, South African Pulsar Timing Array, Chinese Pulsar Timing Array. And so together we share data and are forming the International Pulsar Timing Array.
Oh, wow. Now, the results that you announced last month at the American Astronomical Society's meeting, those were acquired recently. Are they from a decade ago? I remembered something like 12 and a half years plus more years. So can you clarify how much data was actually obtained to make this announcement? And then where does the future see us going in this particular direction?
Yeah, so at the American Astronomical Society meeting, we announced that we discovered the first hint of a gravitational wave background. So this took 12 and a half years of data, and that means hundreds of people have been timing these millisecond pulsars. In this instance, there were 45 millisecond pulsars that we used. And their length span from 3 years to the full 12 and a half years, which means, people have been going back to these pulsars roughly every 2 weeks for 12 and a half years to time them, to look for gravitational wave signals. So I'm not sure you can be too upset with us, Brian, for, having a hint of a signal after 12 and a half years of doing this experiment, and timing every 2 weeks.
Right. Now, my soon-to-be 5-year-old always wants to give me a hint of what I'm going to get her for her birthday. What does it mean, a hint? What does that mean? Is that like a skosh or a little tidbit? How do we quantify what a hint means, and why do you use that particular claim rather than saying detection or evidence?
Right. So detection and evidence for are very technical words that have very strong meaning in the scientific community, and we're not that confident yet. And so what we found in the 12 and a half year data is a signal that's present in all 45 of the millisecond pulsars. And that signal has the same amplitude in all of these 45 millisecond pulsars. Now, we've tried to figure out if something else could be generating this signal. And so far, we've come up short. So we can't think of anything else that could be generating the signal, but that doesn't mean that there isn't something else. So what we expect when we do eventually make the detection is that there are two parts to the detection story. The first is seeing this common amplitude, this common low frequency signal in all the pulsars. Now, these millisecond pulsars are scattered about in our own galaxy, and they're thousands of light years away from the Earth and from each other. So having a signal that's present in all of these pulsars at the same time is really exceptional, right? And one of the only physical processes that could be generating that would be this gravitational wave background. And we believe that this comes from the cosmic merger history of supermassive black holes. So the first step is this common amplitude. Now, the second step is looking for this signal that you get when you cross-correlate all of the millisecond pulsars. Now, according to Einstein's theory of general relativity, there is a quadrupolar type shape. So it kind of, you start up and it goes down like a cosine, but it doesn't quite come up again to the same level that it started. So there's this distinctive shape, and we call it the Hellings and Downs curve. And when we cross-correlate all of these millisecond pulsars, we expect this shape to emerge from the data, these spatial correlations. So if two pulsars are nearby to each other, they'll be positively correlated. And that means that if they move like this at the same time. Now, if they're negatively correlated or anti-correlated, like two pulses separated by 100 degrees on the sky, then they would move like this with respect to each other. So they'd be anti-correlated. And so this Hellings and Downs curve tells us how all of these different pulsar pairs should be correlated if they're under the influence of a gravitational wave background. We have not seen that part of the signal yet. So we've seen part of it, what we believe to be part of it, But the second part is what we definitely need in order to have a smoking gun kind of detection of the gravitational wave background. Now, for anyone who's studied statistics on the call or has ever placed a bet at a roulette table, right now we believe that the evidence for there being some common signal in the pulsars, and it's not just some intrinsic noise in the pulsars, that the odds of that are about 10,000 to 1. So I'm definitely putting my money on that, right? But the odds of that common signal also having these spatial correlations that we expect from a gravitational wave background right now is about 3 or 4 to 1. So good odds, but not really convincing enough to have a press conference and, say that we've made the ultimate detection of a gravitational wave background. So we think that we're getting close because we've seen part of the signal, but we need about 2.5 or 3 years more data in order to really be sure, in order to see those spatial correlations that are emerging that are predicted by general relativity.
Oh, very good. So just a reminder to folks that are listening on Clubhouse, we're also live streaming and recording to YouTube. You can catch that there with some more information about Chiara. And we are, for those of you on YouTube that might want to ask a question with your verbal abilities, I will take questions in just a bit. I do have a question on YouTube from one of my listeners, American Magna. He is, or she is asking, how has the signal changed at all, even by the same amount in the last 12 years? Has there been noticeable variation or time variability, or has it been relatively consistent over the last decade plus?
What a great question. So the signal itself has a different amplitude at different frequencies, right? And we call that a spectrum. And we haven't been able to get our detector down to the level where that signal exists until now, where we've discovered part of the signal, this correlated amplitude, but not yet the spatial correlations. And so it's this interplay between what's generated in nature, right? This gravitational wave background that comes from potentially the cosmic merger history of supermassive black holes, and our ability to get enough pulsars that are sensitive enough to bring our instrument, down to a sensitivity where we can detect that signal.
So I think I'm going to take another question. And those of you on Clubhouse, please feel free to raise your hand. I'm happy to take you up on stage while I am also asking all my questions of my friend Chiara. There's another question of, can you reveal more about the properties of these mergers? Someone's asking, could you see Hawking radiation? Are there other features in kind of the black hole or merger history that would maybe have some impact on our understanding of GR, or perhaps of our understanding of at least the statistical behavior of these objects? Learning more about their intrinsic properties rather than them as a collective.
Brian, you have a very intelligent audience. This is
do.
a fantastic question.
I do. Well, they rise to the occasion.
Question. I didn't plant this question,
no,
to be
it's
clear.
Not. So it's okay. Another Mingarelli. I don't know. It must be some other, just a coincidence. No, I'm just kidding. Keep going.
I was going to say, is it my dad? It's my dad. Okay. Right. So absolutely, yes. Now, I was telling you a little bit earlier that you have this amplitude of the gravitational wave background that's a function of its frequency, right? So it should be some sort of tilted line like this, right? We call it a power law. It really just means that the amplitude scales like the frequency to the -2/3. Now, that's true if black holes are circular when they're emitting these gravitational waves and that nothing else is interacting with them. However, we know that supermassive black holes in these binary systems are in the centers of galaxies, and they're surrounded by gas and dust and stars. So if stars cross the orbit of the binary and are slingshot out, that's going to take away some energy from the binary. And that energy is not gravitational waves. So in fact, it changes the separation of the binary in a different way than gravitational waves do. So if stars are the dominant way that these supermassive black holes are merging at very low frequencies or very wide binary separations, that'll change the shape of this strain spectrum. That's what we call it. But it's really just this kind of behavior that we think should be a straight line and makes it turn over at very low frequencies. Similarly, if your black holes have an accretion disk around both black holes. We call it a circumbinary disk, but it just means that there's an accretion disk around both black holes. They're in the middle. That can torque the binary, and that also takes away energy and angular momentum from your system and causes the black holes to merge more quickly than just gravitational waves alone. So both of these processes can leave imprints in what we measure when we measure the gravitational wave background amplitude as a function of frequency.
Very nice. So next, we're going to take a question from the audience on Clubhouse, and we have Eric and Miguel Yeti Tears, aka Yeti Tears Miguel Tully. And first, we have Eric. Eric, do you have a comment, question, or topic for Chiara?
Just have one question. How do you confirm that dark matter isn't responsible for some of the effects and delays that you're seeing?
That's a great question. So dark matter wouldn't have the same structure that we see when we cross-correlate the pulsar. So I was talking a little bit earlier about this quadrupolar type shape we expect to see when we're cross-correlating the millisecond pulsars. Dark matter wouldn't create that distinctive shape. However, you'd be correct in thinking that, dark matter has a gravitational field, and as a pulsar pulse traverses the galaxy, that could cause a timing delay, right, from that one pulsar on its way to the Earth. That's absolutely right. But that time delay would not be the same in all of the millisecond pulsars you're timing, and it wouldn't have that spatial structure that Einstein tells us should be there. So for an individual pulsar, absolutely, that's a really interesting way of trying to map the Milky Way and its gravitational potential. It's a really interesting idea. But we're sure that what we're seeing right now is not due to dark matter because it doesn't have that, because dark matter wouldn't have that quadrupolar type shape. And it would be different for all of the pulsars in the array, depending on what the local structure would look like.
Very good.
Awesome. Thank you.
Thank you, Eric.
Great question.
Yeah, we have the brightest minds in the multiverse. And the only thing I pride myself on, Chiara, is that I invented Clubhouse streaming for scientific podcasts, interactivity, as well as taking it live. I mean, there's lots of great people that do wonderful conversations with folks all over the internet, especially in science. I'm not the only one, but I love the fact that my audience can interact with my guest. Because how often is it you get somebody as great as you? In fact, Chiara, you'll be interested to know that someone by the name of Michael P. says the following uncontroversial statement: Chiara is awesome. Smiley emoji with sunglasses, Chiara. You should be so thrilled. Hope you can feel that. I don't know who Michael P is.
I don't have any sunglasses here. I have my regular glasses, but there's the glare. So let's just pretend these are my sunglasses.
That's right. You must be a nerd like me. Chiara, here's a really physics professor. That's right. You just like I aspire to be someday. Okay, Ibrahim is asking a question about the computational requirements. This is a cool question. I was interested too. What kinds of computation? Why are you using the CCA, the full power of the CCA, or are you using it? What kind of computing power? If I want to do it at home on my Motorola flip phone, can I do it?
Your Motorola flip phone? Oh my goodness! I don't think that your Motorola flip phone could do it. Maybe if you had a BlackBerry back in the day.
Oh, you Canadian, you.
Exactly, right? Go Rim. So let's see. Computing resources. So I use computing resources differently, like in my own personal research, than what we use for these big gravitational wave background searches. And that's also different from what other people at CCA use the computers for. So in my personal research, what I try to do is create 100,000 versions of the local universe and try to figure out the statistics of which local galaxies can host supermassive black hole binary systems, for example. So my computations are what we call embarrassingly parallelizable. So, one realization might take 5 minutes, but if I have 10,000 cores, everything can take 5 minutes, right? It just depends on how many times I can run this simulation over and over and over again to get this large number of statistics. Now, with the NANOGRAV calculations of the gravitational wave background, and I should say this paper was led by a postdoc called Joe Simon. There you have these large Markov chain Monte Carlo analyses that are taking place. And not only do you have 45 millisecond pulsars that you need to solve for their intrinsic red noise, for example, but they have lots of underlying parameters. Each pulsar has almost 10 different parameters in itself to solve for, and the amplitude of the gravitational wave background, and that frequency dependence that I was telling you about that goes like frequency to the minus 2/3 for supermassive black holes. But you can leave that minus 2/3 as a dependence to solve for, to say, well, what if I'm completely agnostic, right? What if it's not minus 2/3? What if it's something else? I'm going to also solve for that parameter. So you have these huge MCMC chains that can take weeks to even longer, potentially longer, to converge on an answer. So that's how we use supercomputers in that sense. And at CCA, I have some colleagues who work on large cosmological simulations like Illustris, Eagle, Simba, and those just basically take as much computing resources as you have, right? That just kind of just spreads out and takes everything that you possibly have available. So I like to tell my students that for us, our work is going to take, for three to 4 weeks per year. For my personal research that I lead, I'm going to saturate all of the CCA computers, and then we analyze that data for the rest of the year, and then we come back. So
it's good to have
we have a nice mix of people who use the resources in different ways, and that way everyone gets along.
Right, and no computing resource is wasted. Question from Jose: could you detect longitudinal gravitational waves in the background if they exist?
Absolutely. So these would be extensions to general relativity, and they would have different correlation structures. So you're clearly an expert. So I'll tell you a little bit more information. So general relativity have these plus and cross polarizations, right? Which means that's how gravitational waves can change the fabric of space-time. You can also have breathing modes, right, in these extensions to GR. So you have plus and cross and a breathing mode. You can also have, in other theories, gravitational waves that extend space-time along the way that it's traveling. And that would create something that doesn't look like a typical quadrupolar Hellings and Downs curve. So Sidney Chamberlain, KJ Lee, Javier Siemens have all studied these results and can show you exactly what these different correlation curves look like.
Very good. And we're getting towards the end. We have about 8 minutes left before I have to break off into one of my telecons. Chiara, I thought as an astronomer I'd be on telescopes all the time. I'm just on telecons all the time. It's very frustrating. I know you can sympathize with that. So where do we go from here? When I looked at this Emmy-worthy or Oscar-worthy video that UConn Huskies put out last month, this is just so spectacular. It's on Chiara's website, and you guys should watch it on YouTube. But the implications we might be able to discuss detect with NANOGRAV, you might be able to detect the primordial gravitational wave background. Now you're infringing.
Then we would have beef, right?
Yeah, that's right. Now you're infringing on my I don't care, Canadian or not. That is a shot across my back. So
I would not be sorry if we detected a primordial gravitational wave background, just to be clear.
I would not either. Let 1,000 pulsars and CMB modes bloom. Can you tell me, though, how would that work, and how would you distinguish it from the merger background that you may have indeed detected?
Right. So this, the way that the amplitude of the background changes as a function of frequency can tell you what's sourcing or generating the gravitational wave background. So a primordial gravitational wave background, say these, quantum fluctuations in the early universe that are then through inflation, the whole size of the universe can induce gravitational waves that we can detect. That has a different spectral dependence. So instead of going like frequency to the minus 2/3, a primordial background should go like frequency to the -1. And for the experts, that's what it's flat in omega GWs, like we expect. But you could have other kinds of cosmologies. If you believe in bouncing universes, ekpyrosis or string gas cosmologies, other kinds of exotic physics, then you can have something called a blue tensor index, and you could potentially detect a signal that is visible in the pulsar timing array part of the spectrum and not necessarily visible in, or could still be hidden in terms of the LIGO gravitational wave background. So instead of having something that's flat, it could tilt up and be blue in that sense. So if things tilt up, they're called blue. If they're tilt down, they're called red. But yeah, you could have these blue tensor indices, so that could be really interesting too.
Yeah.
But this is far from standard cosmology, as you know.
So there is a question by Ivan on YouTube that asks a question that's kind of painful for me to suggest, but as you know, there have been claims of detections of the primordial gravitational wave background that were later found to be contaminated by dust. I happen to know a little bit about that. Yes, Chiara, it's true. But
that was in the introduction to my PhD thesis, by the way. I was so excited. I wrote like a whole section on bicep 2. I was like, this is so cool.
You have to retract your PhD then, Chiara. I'm sorry to tell you. No.
I know. The PhD police will come and take it away from me.
Ivan is asking, could there be any local change in the ISM? Maybe the dispersion measure, something like that. Could that explain the signal? Is that a big systematic?
It's a big systematic and something that we think about a lot. In fact, in NANOGRAV, there's an interstellar medium mitigation group. All they do is think about this. So the interstellar medium could indeed be a correlated signal between all of the pulsars, or many pulsars in a particular line of sight, or just depending on if there's like a blob of something that's affecting multiple pulsar lines of sight. It doesn't have the quadrupolar type shape, right? But it could induce some sort of common time delay. And so something like that, we can't rule out at the moment, even though we think that that's really unlikely. And so again, we're not claiming a detection until we can find this quadrupolar type correlation that we call the Hellings and Downs curve. Right. But yes, it's a galactic scale gravitational wave detector. We can't turn off the pulsars and turn them on again and see if they behave differently. We don't have a nice vacuum cylinder that goes all the way to the pulsar to make sure that there's no gas and dust along the way. So we can learn a lot about the interstellar medium. But as your very bright listener points out, it can also be a pain.
Yeah. So last question from YouTube. I'll take one from Clubhouse, one more from YouTube, and then we have to break off. Actually, I have one question as the host of the Into the Impossible podcast. So find us on YouTube. If you're on YouTube, give it a thumbs up. Give me a subscribe. Tell me what you learned from this episode, and hopefully we'll get Chiara back if we get enough groundswell. I promised her I wouldn't tell her how many hundreds of people are watching her right now. Okay, last question from Ibrahim on YouTube is also very interesting. Could you tell anything about the effort to map the Milky Way's gravitational field and whether or not NANOGRAV is participating in that effort? To map out, presumably, influence of dark matter and other features in our galactic gravitational potential?
It's a really interesting and exciting project. Right now, it's not one of the key NANOGRAV projects, although there are a few scientists who are involved in doing that. But these are more of our pet projects right now, not one of the flagship results that we're really putting a lot of person power into, like gravitational wave background detection. And then after we detect the gravitational wave background, it'll really be a background. In fact, it's a bit of a misnomer. Right now, it's the foreground signal. It's what we're looking for. And hopefully one day it'll be a background signal that we're trying to subtract.
Right.
And then we can look for things like anisotropy in the gravitational wave background. And this will look a lot like one of the CMB maps. Maybe you even have one of those beach balls in your office, Brian.
I do.
And then we can find individual supermassive black hole binary systems, or when we can eventually constrain how that amplitude evolves as a function of gravitational wave frequency, then maybe we can say, it's 90% supermassive black holes and 10% cosmic strings. Right. Or maybe it's, 80% primordial because that's just the way the universe is. And the rest of it is from like this puny population of supermassive black holes. But really, it's all like porosis.
Very good. Lindsay Forbes, who's a good friend of the show, just says, Dr. Chiara, you explain this complicated stuff so well. And I love the way you use your hands to explain the signals. Thumbs up. So that's a tip to folks to yeah, she's, I don't know, you might be part Italian or you might be Jewish. I don't know. But we use our fingers and hands a lot, at least in my culture. Chiara, thank you so much. There's one from Ernesto. I have to take it. He's a good friend of the show as well on YouTube. Is there a noisy or random nature to the gravitational wave background pattern, or does it manifest some regularities?
What a great question. So the gravitational wave background itself is stochastic, or at least we believe it to be stochastic, which means random, right? And so this happens because supermassive black holes, over their cosmic merger history, they evolve really slowly at these very low frequencies. And so there's a pileup of sources. They're all in this 1 to 100 nanohertz range where we have our experiment at the same time. And then eventually they take off and merge. But for example, if you have 2 billion solar mass black holes that are merging and they're equal mass, let's say, they are about 25 million years from merging at 1 nanohertz, right? 25 million years to get across the pulsar timing array band. Now compare that to LIGO, where their sources are in their band for a fraction of a second. 25 million years. So you can get a lot of supermassive black holes at low frequencies over 25 million years. And that's what creates this background. Now, even though it's a stochastic signal, it has things like an amplitude and this spectral dependence. And that means that we can, define some global properties of the background. Even though we can't resolve individual sources, we know things about the ensemble of supermassive black holes that we're looking at. So this amplitude, this frequency dependence, for example.
Very good. Okay. Miguel, do you have a quick question on Clubhouse? Otherwise, I will finish up. Or maybe Rockwell, if you have a question for Chiara, I'm inviting you guys up. And Azada, if you would like to ask a question, I'll invite you up. So this is Clubhouse. We got to get Chiara on Clubhouse because, as Michael is saying on YouTube, definitely have her back. This is great mind-bending stuff. She is bending my mind more than gravitational waves bend space-time. Wow, Michael.
Well, that's about 1 part in 10 to the 15, so it's not actually a big compliment.
You just insulted her. Michael.
That's 1 part in a million billion, Michael, just to let you know.
Try harder, Michael. Let's see, Miguel, you're up there. You got a quick question for Chiara before I ask the final question to her.
Yeah, how are you, Chiara?
Go ahead, Miguel. She is listening.
Just wanted to know, what is your most cherished piece of memorabilia from your career?
Oh. Can I go get it? It's on the fireplace, man. I'll show you.
Go get it. All right. She is, for those of you not watching on YouTube, take the opportunity. Go to YouTube. Yeah, I see you there. Thanks, my brother. So Chiara's back. Here she is. And memorabilia. Go to YouTube, Dr. Brian Keating, if you want to see it live. Oh my gosh, what is that?
Yeah. So the first year of my PhD, I worked on experimental gravity. I was looking for compactified extra dimensions predicted by string theory. And this was at the University of Birmingham. And I'm clearly a theorist, but when I got to Birmingham, the experiment that I was supposed to use to look for compactified extra dimensions was not built. So my then supervisor told me to design an interferometer that could make nanometer surface corrugation measurements so that we could make sure we weren't detecting the Casimir force, that we were detecting torques from extra dimensions. So as a good theorist, I was terrified and then decided to get to work. So I built and designed a Mach-Zehnder interferometer that could do nanometer surface corrugation measurements. And part of that was doing a machine class where I machined all of the components for my interferometer. And this is one of the components that I made. So I made absolutely everything here. The screws, the threading inside. I used a lathe to machine all of the aluminum. This holds a laser diode right here, and that you can screw into place with this screw. There's a lens here to focus your beam. And then you can take off the front to put in a new lens. And then this, attached to the top of my optical tabletop experiment. And I ate lots of Thor snacks while I Thorlab snacks.
Those of
While
us who build things know
yeah.
exactly what Chiara is talking about. That is,
Yeah, I think that's the most cherished thing that I have in terms like a physical thing.
I have a rule against inviting theorists into my lab, but now I know I will be safe to invite you into the laboratory. I actually had Sir Roger Penrose in the lab last year, and we're still
Did he break something?
We're still cleaning up the debris. Yeah, this is pre-Nobel Prize, so afterwards, now we can't even fit his ego in. No, I'm just kidding. He's
we're not.
All right, so we've got all these compliments. They want to have a show just with you for another hour. We're gonna make that happen. Chiara just reassured me in humanity, gave me hope that there are intelligent, hardworking people trying to understand the secrets of the underlying universe. That's really beautiful, Ibrahim. Thank you so much. Lindsay says you got to get it back. Javier says extraordinary talk for the non-specialist. Thanks. I want to ask you one last question, if you are willing, in the remaining minute that we're over. I want to ask you, Chiara, a question I ask all my guests, from Nobel Prize winners to billionaires to Olympic athletes to astronauts. I had an astronaut on recently. I'm going to ask you this question, and I apologize for not alerting you ahead of time, but maybe you watched some of the video homework assignments I sent you. I ask all my guests.
I didn't get to the end of them. I wish I did now.
All right, now you've got your homework set up. I want to ask you, the title of this podcast is Into the Impossible, and it derives its name from Sir Arthur C. Clarke, who had all these famous aphorisms, one of which is, any sufficiently advanced technology is indistinguishable from magic. Another one is, for every expert, there's an equal and opposite expert. And the third one kind of relates to advice. I want to hear your advice to your former self. And it goes as follows. The only way of determining what is possible is to venture beyond the limits of the possible into the impossible. And that's the name of this podcast. I want to ask you, as a younger person, maybe 15 years ago, 10 or 15 years ago, what advice would you give to a younger version of Chiara to help her have the courage to go into the impossible?
Goodness. What would I tell myself? I would tell myself to hang in there, that nobody has all the answers and everyone is struggling just as much as me. And that, even people who you think have it all together and that are brilliant, they're just people. There are some people who are more famous than other people. There are some people who are smarter than other people, some people who are kinder than other people. But no one is better than you, and everyone struggles, and everyone, has a whole history of things that you don't know anything about that's affecting them every single day. So I would tell myself to hang in there and do your best, and you can always be proud of things, even if it doesn't work out, right? Like my tabletop Mach Sender interferometer. I didn't complete the experiment. I started working on gravitational waves instead, and it's going pretty good.
The world is richer for that, and the universe as well. Chiara, I want to thank you so much. Dr. Professor Chiara Mingarelli, the University of Connecticut, Stores, Go Huskies, my mom's alma mater, and also of the Flatiron Institute, the Center for Computational Astrophysics, where
Go Team Simons.
Chiara, we all are huge fans. Obviously, we got to have you back. Maybe in a few months you'll grace us again with your presence. And I want to thank you so much from the bottom of my heart for going into the impossible with my audience.
Oh, thank you so much for having me. I'd be happy to come back.
Okay. Bye, Chiara. Bye, everybody at Clubhouse. We'll do another one later on this week, maybe with Kamal Ravikant. We're trying to get him on. Bye, guys. Take care. Bye, Chiara.